The very beginning of this, we are summarizing using your magic chart. Okay? Way back in Unit 3, we did applications of derivatives. If the first derivative was positive, what did that tell us about the original? It was increasing. If the first derivative was negative, what did that tell us about the original? Decreasing. And that told us absolutely nothing about the second derivative. Okay, the second derivative does not give us answers on that. Okay? Where it switches from either increasing to decreasing or decreasing to increasing, we had specific points. Anyone remember what we called those? That's on the second one, points of inflection. Relative maxes and mins. Okay. Then we moved on and we talked about the second derivative. In the second derivative, if that was positive, what did that tell us about the original? That was concave up. And if it was negative, the original was concave down. And it gave us one additional piece of information. Because it's the derivative of the first derivative, it told us where the first derivative was increasing or decreasing. And in between, where it switches from positive to negative or negative to positive, we called those points of inflection. And that was like a major part of Unit 3. That was like a massive summary of the first 2 or 3 lessons that we did. We also talked about critical numbers. Critical numbers helped us find relative maxes and mins, but they were not always relative maxes and mins. How did we find critical numbers? Derivative was equal to 0 or undefined. Undefined we really worried about when it was like a fraction. The bottom of the fraction equals 0. That's when that came up. And then we also distinguished between absolute maxes and mins versus relative maxes and mins, okay? So to go through our steps for that. To find absolute maxes and mins, just to give you a little review. 1, we found the critical numbers, which we just talked about finding. 2, we evaluated f of x, the original, at critical numbers and endpoints. Okay? So we plugged it in, and the biggest number was our max, the lowest number was our min. The difference between absolute mins and maxes and relative mins and maxes is that the absolute, we evaluated the original, and we had an interval. The relatives we did not have an interval for. We still had to find the critical numbers. But then on this one, we had to do a number line. Remember the number line where we did the ends of the graph and it was positives and negatives and we labeled the pluses and minuses for that? Okay. So we did a number line for our derivative, f prime of x. We graphed our critical numbers and we did like a graph of what that looked like. I'm just making one up here to give you a little visual. We labeled our number line with positives and negatives, and this then told us where the original was increasing, decreasing, where we had relative mins and maxes. Okay? The second derivative test helped us also, in a second way, tell whether we had relative mins and maxes. So the second derivative test told us this. If x is a critical number, then if f double prime of the critical number is positive, that told us that it was concave up, and therefore we had a relative min. If f double prime at the critical number was a negative number, that told us our original was concave down, and therefore we had a relative max. We used the second derivative test when we did not have enough information to do a full number line on this. It often happened with tables of numbers, and we had just a little bit of information about f of x, f prime, and f double prime. Within Chapter 3, we also talked about the mean value theorem. That was our other big one, and then we started summaries. We did IVT, MVT, okay? MVT had 2 conditions. In order to apply MVT, it had to be first what? Continuous, secondly, differentiable. So you could take the derivative of it. If it was both continuous and differentiable, the short version of this was, there was at least one x value at which the instantaneous rate of change equaled the average rate of change. That's the short version. You could have also been told the slope of the tangent line equaled the slope between two endpoints. That happened a lot on online quizzes. Or third was tangent line parallel to secant line. Our equation for it was that f prime of c equaled f of b minus f of a over b minus a. Give you a minute to copy that down. Okay. And Rolle's theorem wasn't just a small extension of that. Anyone remember what Rolle's theorem said? It was the specific instance that if f of b equaled f of a, what did we know? Yeah, then f prime of c somewhere equaled 0. Somewhere in that interval between b and a. So f prime of c somewhere between b and a would equal 0 as well. But that was just an extension of that. Something that came up quite a bit, and just a random note on the side, we had the tangent line that was below or above the function. We talked about that several times. It came up in several tests, actually. And we talked about the only way to tell if the tangent line was above or below the function, if you could make a statement about your f double prime of x is positive or negative. Okay? If f double prime is positive, that meant that the original function was concave which way? Up. If the original function was concave up, the tangent line would be above or below the curve? Below, because it had to fall underneath it, right? If f double prime was negative, therefore the original was concave down, and my tangent line would have had to be above the curve. That came up several times, and we always tried to reason it out in different ways, but that was the only way we could have reasoned it out. Okay. Summary, short and sweet.